Hey guys, welcome back to our Learning Unreal Engine tutorial series. In today's video, we're going to walk through some different methods of flow control in blueprints. We'll start with the basics like branch nodes and work our way up to loops and switches. Let's go ahead and jump right in. Starting off, we have our first module here, which is the branch node. Branch nodes perform if-else execution based on the current value of a Boolean variable. If that variable is true, it will execute A pen, and if it's false, it'll execute the B pen. The branch node is the basic building block of flow control in Unreal Engine blueprints. Anytime you need to use an if-then statement, you'll probably find yourself wanting to use a branch. Here you can see we've got a custom function set up to change the color of our target sphere, the purple sphere there, based on a Boolean variable called isRedButton. So is the player interacting with the red button? If that's true, we'll change the color of our material to red. And if false, we'll change the base color to blue. So let's go ahead and take a look at that in our project. As you can see, when I step on the red button, the execution pin on top of the branch will fire because our isRedButton variable is true. And you can see the execution flow into the branch node and then out through the true pin. If I step on the blue button, then that isRedButton variable will be false, and we'll set the color to blue. These can obviously be used to test many things, including much more complicated conditions. One reason you might use a branch node in a game is to say, if your player takes damage and their health goes below 0, then the player loses a life. If that player has no extra lives and loses a life, then game over. Another example might be if a weapon clip is being reloaded and it is depleted, then reload the weapon. If it's not depleted, then tell the player that the weapon cannot be reloaded. Up next, we'll take a look at the doEnd node. The doEnd node will execute a task n number of times and then halt execution until a pulse is sent into its reset pin. So every time that it receives a pulse, it will allow the execution to flow through it until a certain number has been reached, and then it will stop execution until you've reset the node. Taking a look at our blueprint example, we can see that we've got an integer value for number of activations, controlling how many times, and it's currently set to 5, how many times the doEnd node will allow execution to continue. Once execution flows through, we will set our current counter based on where we are in our doEnd, and then we'll run a sequence node to accomplish several different things. Making sure that the button can't be activated again for a moment, determining the next scale of our object, the next location of our object. If our current counter is less than the number of maximum activations, we'll update our text. And if we've reached our maximum, then we'll display a reset warning. Finally, we'll run a timeline to implement all of the scale and location information that we set above, and transform our sphere. Once we've done this 5 times, It won't allow it to continue until we reset. And our reset logic is coming from this graph over here. And what's going on here is just resetting a bunch of values and running another timeline to reverse what we did before. Let's go ahead and take a look at it in our project. When we step on the button, it will start to move and scale up that sphere and almost inflate it like a balloon. You can execute it one time, and you see the execution flow through our do in. We can do it another time, a third, a fourth, and a fifth, at which point our instruction text says it needs to be reset because we've reached our fifth execution. And if we try, the execution will not flow past that do in node. However, I've got our handy button here for resetting. And it fires the reset pulse and allows us to continue again. You can reset at any number of executions. You don't have to reach the maximum number. And it sets everything back to 0 and lets us continue to play. Do in nodes can be helpful in a game setting. Let's say if you have a carnival game where you only get 5 attempts at playing, and then once you've used up your 5 attempts, you have to purchase more, which would be your reset button. Another example is perhaps a boss has 3 big attacks that they can do. And then they cannot attack until the next phase of attacking after, say, a puzzle phase or some sort of action phase. Similar to the do in node is the do once node. Do once nodes function exactly the same as do in nodes, except in will always be set to 1. Taking a quick look at our blueprint, you'll see that the setup is very similar. We have an execution pin coming in, a reset pin, and then an output pin. So what we're going to do is one time we will allow the player to run the sequence node that spawns some cubes and gives them some physics, and then updates our text and reset. And again, we've got some logic over here for what to do when resetting the scene. Ending with an execution pin, flowing back into our do once reset, and allowing us to continue. So let's run that in game and see how the execution flow works. When I step on the button, we get execution flowing through. It spawns our cubes and cannot be executed again. Anytime I try, just like with the do in node, once it reaches its maximum, it'll block execution. But we can always reset and play again. Do once nodes can be very handy for blocking players from interacting with things too many times. So let's say you have a vending machine and you don't want the player to be able to make a double purchase and spend double their money to only get one thing out of it. You can use a do once to temporarily shut the machine off while it's handling the logic, and then reset it when the player should be able to purchase it. Moving on, we have a flip-flop node, which alternates between 2 output execution pins every time that it fires. The first time it will execute A, then B, then A, then B, and so on. It does include a Boolean data pin to track when you're executing A, which can be very helpful depending on what you're using it for. Taking a look at our blueprint, we can see our flip-flop node here with execution pin flowing in, and then an A output and a B output. When we're working with A, we will set the purple light and purple cube to hidden in-game, and invert that to set the green light and green cube to be not hidden in-game. On the execution pin B, we will do the opposite, which will give us a false Boolean out of the is A, meaning the purple light and purple cube will turn on, and the green light and green cube will turn off. We've got some other stuff here to update some text and change the color on our text there. So let's go ahead and demo what the flip-flop node looks like. So there's our A output, and then B, A, B, A, B. The flip-flop node can be somewhat limited in its usage because it's not very flexible, but it can still be useful for things like turning on a light with a switch. It's just a matter of finding the right use case for it. Our next module that we'll talk about is the gate node. The gate node allows you to open and close incoming execution based on a current state that determines whether the execution can pass through the exit pin. In our script, we'll be feeding in a auto-playing and looping timeline. So basically just a constant flow of execution into the gate node. You can see that it's currently closed, so it's not allowing anything through. And we've got some logic here to open and close it based on whether the player is currently on the pressure plate or trackpad. And once we open it, we'll tell the sphere to move to a location to basically track the player left to right. In action, what that looks like is stepping on the trackpad will open the gate and allow execution to flow. Stepping off will close the gate and cause it to stop functioning. A gate node can be very useful in a lot of different situations. So for instance, if you have a trap that deals damage over time, but only once it's activated or only once a player is doing a certain thing, that would open the gate on the damage. Up next, we have the multi-gate node, which, despite its name, acts almost nothing like the gate node. A multi-gate instead will receive an execution pulse input and direct that execution to any number of possible outputs. The multi-gate node does contain options to route ongoing execution sequentially or randomly, and it can be made to loop. Taking a quick look at our blueprint example, we have another timeline that will start to fire once we step on the pressure plate, and it will loop over time, feeding an execution pulse every half second into our multi-gate. Here's our option for whether it will be random and whether it will loop. We've currently set those both to true, so it will pick a random output execution and fire the pulse out to a macro that will bump the cube attached to that output up by 20 in the Z direction. Again, we do have a pin for resetting the multi-gate, which sets it back to its original state, which will happen when we step off of our pressure plate button. So keep an eye on our multi-gate as we step on the button, and every half second we'll send a new execution pulse out to a random output. In the project, you can see the cubes randomly getting bumped in the Z direction by 20. And functioning exactly as we would expect. When we step off, everything resets, and we go back to square one. Multi-gates can be very useful when you need some extra options on running a sequence of events, because you have the controls for randomness and looping. One example might be a boss that has 4 unique attacks that can fire in any order, or a player that has a complex spell with multiple effects that happens sequentially and continue to loop until a certain duration has elapsed. Up next, we have the for loop and for each loop, which are both combined into a single module here. First, we'll talk about the for loop, which works like a standard simple loop in programming. It fires once per index and sends an execution pin out on each iteration of the loop body. The number of times it fires will be determined by an integer value that you can feed into the for loop, and it will continue until the last index. The for loop also gives you another pin for when the loop is completed. Fire out one last execution pulse and do something else. Here in our blueprint, you can see that we've got 2 for loops being used. One when we begin play, which is already fired, to run from index 0 to index 16, so it'll run 17 times. And each time on the loop body, it'll spawn a bobble actor and add that to an array for us to track. When we step on the button, it'll run it another 9 times from 0 to 8 and do the same thing. For demoing this behavior, let's also talk about the for each loop. For each loops work very similar to the for loop, except instead of looping a set number of times determined by an integer value, it will iterate over the elements of an array. For each loops will also give you access to data pins that carry a reference to the current element that you're working with, as well as the current array index that you can use inside the loop body. Here we have a couple examples of a for each loop in use. The top one, depending on which color button we step on, will set a color to be checked, and then for each element of the baubles array, we will take that bauble and run a custom function on it to drop it if it's a certain color. So if we step on the blue button, it will drop all of the blue baubles to the ground. Red will drop the red, and yellow will drop the yellow. Similarly, when we step on the black button, for each bauble in the array, we will destroy that actor and clear it from our array. So let's go ahead and activate this and see how it works. First, we'll monitor the for loop. And unfortunately, it fires very fast, so it looks like a single execution pulse being sent out, but it is actually happening 8 different times. Well, 9 different times. Each time we step on the button. Taking a look at our for each loop, when we step on the blue, for each element in the array, if it's blue, we will drop it to the ground. Yellow will work the same way, and you can see the execution pin fire on the bottom path of execution. And red the middle. Finally, we can clear all of our baubles by stepping on clear all. While loops are a little more complicated than the for loop and for each loop. They will execute the logic within their loop body until a certain test condition is determined to be false. The loop will reevaluate that test condition after every iteration of the loop body. As a best practice, the loop body should be able to alter the test condition to make it false in some way to avoid infinite loops. Infinite loops will either severely impact the performance of your game or more likely crash the project altogether. Taking a look at our blueprint, our condition is that no actor has been spawned close enough. So as long as no actor has been spawned close enough, the while loop body will continue to spawn more actors. Once it has spawned an actor, we run a sequence of events to add it to an array, change its base color to white, and test whether that bauble is within 75 units of the player. If it's within 75 units, we will set our condition to false to stop the while loop from running. And we will set that element, that bauble that we spawned, as the closest one. Once the while loop has completed, we get an execution pin running down here to a couple of for each loops that will change the base color to yellow on all of the baubles in the array, and then change the base color to pink for our closest bauble, and update our text. And then after a short delay, drop all of the yellow baubles to the ground. Once again, like the for loop and for each loop, this will function very quickly and look like a single execution pulse, but it is going to fire a certain number of times until our test condition has been met, and then the completed pin will run. Let's go ahead and test it out. There's our pink and all of our yellow balls. And when we step off, they'll all be cleared. Once again. And again. So as soon as we get that pink one that's close enough to the player, within 75 units, we stop spawning anymore, and then run the rest of our logic to indicate that the module has fired. While loops can be very useful in validating that several objects are what they say they are at once, or validating that something is the case with a set of objects. They can also be used to sort through arrays and step through them to check certain things, and run a bunch of calculations until you meet a certain condition. Finally, we have the switch node, which is my personal favorite of the flow control nodes because it gives you a ton of control depending on what you're trying to do. Switch node allows you to direct execution with more exact control based on the current value or state of a data input variable. That data input could be of type integer, string, name, or a value from an enumerated list. Enumerator switches will automatically populate the output of the execution pins, while other types are customizable and let you add as many pins as you need. Taking a look at our blueprint, we will work with an integer switch, as well as an enumerator switch in just a moment. For the integer switch, as a simple demonstration, based on our counter, if it's 0, we will set our current color to yellow and spawn a pickup with that color. On integer input 1, we'll do a pink pickup, then a blue, and then a red. Each time we step through, we will increment our counter so that we get a sequential behavior. And when we reach our final line, we will set our counter back to 0. Now within this spawn pickup function, we'll make use of our switch on enumerator. So depending on which pickup color we grab, we can set different behavior. Here, I've got them all doing basically the same thing. Setting a color for that pickup. So when we spawn it, whatever color this is, we're just going to pass that along to the pickup object itself. But these can be much more complex, which we'll talk about in a moment. So let's go ahead and demonstrate our integer switch first. As I step on, at integer 0, we get a yellow pickup. Then the 1 line fires, then 2, then 3. As I pick these up, we could have coded some complex behavior in for each individual pickup type, but what I've got it set to do is just change part of our mesh color to match. So there's yellow, pink, red, and blue. Now let's go ahead and watch the same thing happen from within our spawn pickup function, where we can watch our enumerator switch. When we spawn a yellow pickup, the third input will fire. When we spawn a pink one, the bottom input will fire. Then the top for blue. And then the second one for red. As I mentioned, I've got this set up for very simple behavior, but you could code this to say, when you pick up a red pickup, heal by 20 points. When you pick up a blue pickup, heal by 50 points. When you pick up a yellow pickup, give the player a speed boost. And when you grab a pink power-up, make the player invulnerable for 30 seconds. As you might have noticed, as we've been working through several of these modules, flow control elements will often be used together in conjunction with one another to create more and more complex behavior. You might need to run a for each loop that within the loop body is executing a branch node to check a certain thing. And then once you've met that branch node, then you run a switch. And within that switch, you have several more branches and a do once to make sure you're only doing something one time, and so on and so forth until you can build up complex, nuanced behavior for your project. And that's going to do it for today's video on flow control. As always, if you liked the video, give us a thumbs up, and go ahead and subscribe to the channel so you get updates when we release new videos. Our next video will be discussing functions and macros and how to use those within blueprints. As always, thanks for joining us today, and we hope to see you again soon.